Hi, everyone, and welcome to this episode of Foundry Fireside. My name is Lori from the Foundry Communications team, and today I will be chatting with one of the Foundry's postdocs, Tim Kodalle. Tim works with the Foundry's Carolyn Sutter Fellow on materials used in solar cells. All right, Tim, how about we get started with you telling us a little bit about your project?
Thanks, Larry. Yeah, so in the group of Carolyn, we work with in situ characterization of functional material. In situ means that we look at properties of thin films in our case, while these properties evolve, so while we make the films. And in my project, we do that with materials for photovoltaics, so for absorber materials in solar panels. And as you probably know, most of the solar panels you can buy and you see on houses right now are made from silicon. And we are working on alternative materials that can have potential to have better efficiency or other interesting properties in order to populate niches in the markets, or in some cases maybe even replace silicon at the market.
Wow, that's really interesting. So what is special about the solar materials that you are working on?
So we work on perovskites, and that's a compound semiconductor, meaning it consists of like several different elements, and by tuning the ratios of these elements in the final compound, we can tune the properties of the film. And therefore, it's really interesting for so-called tandem photovoltaic applications. That means that instead of just having one solar cell that absorbs like as much as possible of the solar spectrum, we kind of split up the solar spectrum into two fractions and use the bottom cell to collect part of the solar spectrum, and then use the perovskite top cell to use a different part of the solar spectrum. And these perovskites, because they are so tunable, can be like really can be designed very specifically to just absorb the part of the spectrum that we want them to absorb, and then therefore increase the overall efficiency that we can get out of the tandem stack compared to if we only had like a single junction solar cell. So for example, only a silicon solar cell.
Wow. So what's the hope for this project?
The hope for this project in particular is to find out how this perovskite layer grows, so like how this thin film grows, in order to be able to then tweak the growth parameters in order to make it optimized for this application of the tandem photovoltaics. So what we do is we grow these thin films from solution in the lab here at the Molecular Foundry, and we use in situ characterization. So during the film growth, we look at the properties of the film and try to understand how we get from the precursor, so the solution in the beginning, to the final perovskite thin film, the solid film. And by looking at that in real time, like while the film evolves, we can get like a really good picture of the processes, the nucleation dynamics, the growth processes that happen during the process. And by understanding them well, we can then like propose and test other process routines in order to get a better result in the end.
That's really cool. So what makes you most excited about this?
So I think that's a twofold answer. So on the one hand, I'm really excited about the capabilities we have here that we can measure in situ, because a lot of times people can only look at the final result of the process. So they make the film and then they use like a lot of different characterization techniques in order to measure the properties of the final result. And then they build models on top of these final results of what happened during the growth process to get there. And due to the fact that we have these in situ capabilities here, we can kind of skip this black box step and can just directly look at what happens while the film grows. And I think that's really, really cool, because we like literally make little films of how the properties, for example, the luminescence of the film evolves during the film growth. And I think that's really interesting. And then the other part of the answer why I'm really excited about that is, just the application of it, like renewable energies. As we all know, climate change is going to continue to be one of the most important challenges for mankind right now. And I feel like with working on solar materials, we can contribute a little bit to possible solutions to the climate crisis.
Oh, that's really awesome, Tim. So why this research? What made you want to study this area?
Yeah, that kind of directly connects to what I just said. Like I was like, since I started studying physics, I was interested in solid state physics, like trying to understand how materials grow, how crystals grow, how they evolve, how we can optimize the properties of all these crystals in order to use them in everyday applications. And then especially the aspect of renewable energies, like how we can use materials and crystals that exist in nature, and how we can like tweak the parameters of how we grow them in a way to use them to generate clean energy, for us.
All right, thanks. Okay, one last question for you. What's the next big step or big question for your research?
So for my project particularly, we look at two different kinds of tandem solar cells. One is the one that I mentioned in the beginning, silicon, and then perovskites on top of that. And the other one is a mixture of two different materials, chalcopyrites and perovskites. It's not really that important what these materials are, but what is important and interesting to us is that they all have different surface properties, so especially different roughnesses. And as I said in the beginning, we tried to grow the perovskite layers on top of the bottom device in order to harness the solar spectrum more efficiently by splitting up the spectrum that's getting absorbed by the bottom and the top device. And in order to be able to do that, we have to grow the perovskite directly on top of the bottom device, and therefore have to deal with the properties that bottom device gives us in terms of the substrate, right? So if we usually would deposit the perovskite layer and try to optimize it, we would just do that on a very flat substrate in order to just get a really nice and easy start of the growth process. But in this case, we have to deal with the very rough surface of the bottom device. And we use these in situ capabilities that we have now to try and find out how this different surface, like how this roughness influences the growth of the perovskite, and then try to find ways how we can mitigate the disadvantages we may have because of the surface roughness of the bottom device, in order to then optimize the perovskite layer for that tandem junction device.
Wow, that's really interesting, Tim. Thank you so much for spending some time with me today. It was really interesting to learn about your research. And for all of you listening today, thank you for tuning in, and stay tuned for more episodes of Foundry Fireside.